Hello, and welcome to Breezy Sleepy Science. I'm so glad you found your way here tonight. Our journey takes us far beyond our world, into the silent, glowing hearts of the stars themselves. These distant fires are far more than simple lights in the void. Some are so colossal they could consume our entire sun without a trace. Others end their lives as impossibly dense remnants, spinning faster than a hummingbird's wings. And each one is a cosmic factory, creating the very atoms that form your body, this planet, and everything you've ever known. When you gaze upward, you are not just looking into space, you are looking back through time itself. The starlight touching your eyes tonight may have begun its journey millions of years ago. Some of those stars have long since vanished, their light a final fading echo. Yet others will burn on long after our world is gone. If these peaceful journeys bring you comfort, consider liking this video or subscribing to the channel. Sharing your reflections in the comments below also helps other weary travelers find their way here. But for now, your only task is to relax. Let your breathing become slow and deep. Allow your thoughts to grow quiet, to grow light. If you're ready, let's begin. The most enormous stars known to science could easily swallow our entire solar system. The sheer scale of these giants defies all human comprehension. Take the red hypergiant UY Scuti. Its radius is roughly 1,700 times greater than that of our Sun. If it were placed at the center of our solar system, its outer layers would stretch out past the orbit of Jupiter. Even smaller supergiants, like Betelgeuse or VY Panis Majoris, would completely engulf Earth's orbit. These behemoths are rare, burning through their nuclear fuel at a ferocious rate and living only a few million years, a mere blink compared to the billions of years enjoyed by stars like our Sun. Their vast, puffed-out atmospheres are unstable, shedding material into space in great, smoky clouds. The incredible size of these titans serves as a reminder that our own Sun, while immense to us, is quite modest when placed beside the true leviathans scattered throughout the galaxy. Some stars blaze with such ferocious energy that they can, for a time, outshine entire galaxies. While most stars shine with a familiar steadiness, certain rare celestial monsters, known as quasars and hyperluminous stars, can pour out more energy than billions of suns combined. Stars like Eta Carinae, a luminous blue variable, release so much power that they rival the brightness of small galaxies. During an eruption in the 19th century, Eta Carinae flared so violently it briefly became the second brightest star in our night sky, despite being over 7,000 light-years away. Stars of this type live fast and dangerously, consuming their hydrogen at a staggering rate and often meeting their end in a cataclysmic supernova. Their intense radiation pushes outward with such force that it blows their outer layers away in powerful stellar winds, creating beautiful, glowing nebulae around them. These brilliant beacons remind us that a single star can, for a short while, dominate its entire cosmic neighborhood. We are the universe dreaming of itself. When a massive star ends its life in a supernova, its core can collapse into something truly extraordinary, a neutron star. These objects are only about 12 miles across, yet they contain more mass than our entire Sun. The collapse is so violent that it crushes atoms together, forcing protons and electrons to merge into neutrons, creating a substance denser than anything else we know of outside a black hole. A single sugar cube-sized amount of neutron star material would weigh billions of tons here on Earth. Their surfaces are solid, their gravity is immense, and their magnetic fields are beyond comprehension. Despite their tiny size, they shine across the cosmos by emitting beams of radiation or by heating the gas around them with their leftover energy. Neutron stars are the stellar ghosts of once great suns, transformed into spinning, ultra-dense remnants that challenge everything we know about physics. They reveal the astonishing extremes the universe is capable of creating. Among neutron stars, some exhibit even more incredible behavior. These are known as pulsars, and they rotate at mind-bending speeds, often hundreds of times every second. With each rotation, they sweep narrow beams of radio waves or light across space, creating a regular pulsing signal as seen from Earth. The fastest of these, called millisecond pulsars, can spin more than 700 times per second, faster than the blade of a kitchen blender. These pulses are so incredibly precise that astronomers use them as cosmic clocks, rivaling the accuracy of atomic time standards. The initial discovery of pulsars in the late 1960s even sparked speculation that they might be signals from advanced alien civilizations before their true nature was understood. Today, they are used to test Einstein's theory of relativity and to hunt for the subtle ripples of gravitational waves moving through the universe. They are among the most reliable and consistent lighthouses in the cosmos. Magnetars are a particularly exotic type of neutron star, defined by possessing the strongest magnetic fields known in the universe. A magnetar's field can be 1,000 trillion times more powerful than Earth's. This level of power is almost impossible to grasp. It would be strong enough to warp the structure of atoms, tearing molecules apart and rearranging matter itself. When their magnetic fields suddenly shift, magnetars can unleash gigantic flares, releasing more energy in 1/10 of a second than our sun gives off in 100,000 years. These bursts have been detected across immense distances, sometimes briefly outshining every other star in our galaxy combined. Thankfully, magnetars are rare, and none are close enough to threaten Earth. They serve as extreme natural laboratories in space, showing us what happens when physics is pushed to limits we could never recreate on our world. Not every star is a perfect sphere. When a star spins very rapidly, centripetal force causes its middle to bulge outward, flattening it into an oblate or squashed shape. A famous example is the star Altair, which rotates so quickly that its width at the equator is more than 50% larger than its measurement from pole to pole. Such rapid spinning can sometimes fling material into space, forming disks of gas around the star. These distorted suns challenge our mental image of stars as perfectly round, serene orbs. Instead, they show us that stellar lives can be dynamic and turbulent, influenced just as much by their spin as by their mass and age. Rapidly rotating stars may also mix their internal layers more thoroughly, which can extend their lifetimes compared to slower spinning siblings. From our distant viewpoint, they twinkle like any other star. But up close, they would be wildly stretched by the relentless force of their own speed. Hypergiants rank among the most unstable and short-lived stars in the cosmos. Their immense size comes at a great cost. They burn through their fuel so ferociously that their outer layers cannot remain gravitationally bound. Instead, they shed mass in powerful stellar winds, losing the equivalent of our sun's entire mass in just a few thousand years. Eta Karenina, one of the most famous hypergiants, is surrounded by a vast nebula created from material it has blasted into space. These storms of gas and dust enrich the galaxy with elements that will one day form new stars and planets. But for the hypergiant itself, this process is destructive. Its fate is almost certainly to explode in a violent supernova, perhaps even leaving a black hole behind. These stars are cosmic infernos, both beautiful and terrifying, demonstrating the ultimate extremes of what a star can become. A star that wanders too close to a black hole faces a violent and dramatic end. The black hole's tidal forces, the difference in gravity between the star's near and far sides, stretch it like warm taffy. If the star crosses the point of no return, it is shredded in a cataclysm known as a tidal disruption event. The stellar material spirals inward, forming a glowing hot disk as it falls into the black hole. This process releases a tremendous burst of light that can, for a time, outshine the combined light of every star in its galaxy. Sometimes, jets of material are launched outward at nearly the speed of light, broadcasting the star's destruction across the universe. These events are rare, but they provide astronomers with a way to study black holes that would otherwise remain invisible. Each one is a cosmic drama, a brilliant star being unraveled by the ultimate power of gravity. When astronomers observe sudden, intense flares of light at the centers of distant galaxies, they may be witnessing the destruction of a star by a black hole. These tidal disruption events occur when a star strays within the black hole's gravitational grip and is stretched beyond its breaking point. The star's material forms an accretion disk, heating to millions of degrees and shining intensely in X-rays and ultraviolet light. These flares can last for months or even years as the black hole slowly consumes its meal, gradually dimming as the stellar remnants vanish. Observing these events helps scientists measure the masses of black holes and understand how galaxies evolve over time. They also stand as powerful reminders that even stars, those immense, radiant, and enduring objects, are not safe from the deeper, consuming forces that shape the universe. To witness one is to glimpse the raw, insatiable hunger of gravity itself. When two stars in a tight binary system spiral into each other, their collision can be one of the most dramatic events in the cosmos. Neutron star mergers, in particular, release energy not only as light, but also as ripples in the very fabric of space-time itself, gravitational waves. These waves travel outward at light speed, stretching and squeezing space as they pass through it. In 2017, astronomers detected gravitational waves from such a collision, followed shortly after by bursts of gamma rays and visible light. It was the first time humanity had observed both gravitational waves and light from the same cosmic event. These colossal collisions also forge heavy elements like gold and platinum, seeding the universe with the materials that later form planets and, potentially, life. Every ripple of gravitational waves we detect is a message from a stellar collision of unimaginable power, occurring impossibly far away. Not every star remains safely within its home galaxy. Some are flung outward at such incredible speeds that they escape entirely, drifting alone through the vast, dark emptiness between galaxies. These rogue stars can be launched by violent events, such as a close encounter with a supermassive black hole or the chaotic breakup of a star cluster. Once ejected, they wander the cosmic void, carrying their planets, if any survived the ejection, into unimaginable isolation. Picture a solitary sun, billions of years from its birthplace, traveling endlessly with no galaxy to call home. Though they are difficult to detect, astronomers believed there could be countless such intergalactic stars scattered like embers from a cosmic fire. They remind us that space is not a static picture, but is full of motion and chance, and that even something as massive as a star can be cast adrift on the cosmic sea. In the early universe, before galaxies as we know them had taken shape, The very first stars were born. Astronomers call them population 3 stars, and they were likely monstrous, some hundreds of times more massive than our Sun. With no heavy elements to help cool the clouds of gas they formed from, these giants grew rapidly and burned with ferocious intensity. Their lifespans may have been only a few million years, a brief flash on the cosmic timescale. When they died, they exploded in colossal supernovae, seeding the pristine universe with the first carbon, oxygen, and iron, the essential building blocks for future planets and life. None of these primordial stars survive today, but their chemical fingerprints remain in the oldest patterns of the cosmos. By studying those ancient clues, scientists are piecing together the story of how the first light pierced the darkness, transforming the universe from a place of simple hydrogen into one capable of complexity and life. When stars like our Sun reach the end of their lives, they gently shed their outer layers and leave behind a hot, dense core called a white dwarf. At first, these remnants shine brilliantly, glowing with the leftover heat from their past nuclear fires. But over billions and trillions of years, they slowly radiate away that energy, fading gradually into darkness. The final, theoretical stage is called a black dwarf, a cold, dead star that no longer emits any light. None exist yet, because the universe itself is not old enough for even the oldest white dwarfs to have cooled that completely. The concept of black dwarfs belongs to the far, far future, a time when the cosmos will be a much quieter, darker place. They represent the ultimate destiny of countless suns, a silent testament that even the most radiant stars must eventually surrender to time. You are a way for the cosmos to know itself. If the universe continues to expand forever, then its distant future may be a long, slow descent into darkness. Stars will gradually exhaust their nuclear fuel, and no new ones will be born. Red dwarfs, the most frugal of stars, could glow for trillions of years, but even they will eventually fade. Galaxies will grow dim, planets will freeze, and the night sky will empty of starlight. In this vision, often called the heat death of the universe, the cosmos becomes cold and quiet, with only black holes and the faint embers of dead stars remaining. Though this future lies an almost unimaginable distance away, the thought is both humbling and strangely peaceful. The story of stars has a beginning and an end, and we are alive in a moment when the sky is still brilliantly alight with their glow. To gaze upward now is to witness a universe still in its vibrant, star-filled youth. While our universe may one day fade into darkness, some theoretical models in cosmology suggest this might not be the final end of the story. Some ideas propose that our cosmos might experience a bounce or give rise to brand new universes entirely. In those fresh beginnings, the magnificent cycle of stars could ignite once more. The elements forged in our universe could go on to seed the next, ensuring a form of continuity across cosmic generations. Just as stars die and scatter the ingredients for new stars to form, universes themselves might undergo a similar rhythm of collapse, rebirth, and renewal. Though this is highly speculative, the concept offers a vision where starlight never truly ceases. Instead, it shifts across scales larger than we can easily imagine. In this view, the stars above are not just part of our universe, but part of an eternal pattern that could repeat endlessly, a perpetual dance of light and renewal. Not all stars live fast and die young. The smallest ones, called red dwarfs, burn their fuel so slowly that they can shine for trillions of years, far longer than the current age of the universe. These stars are dim and cool compared to our Sun, often invisible to the naked eye from Earth. Yet, they are by far the most common type of star in the cosmos, making up the vast majority of suns in the Milky Way. Because they live for such an incredibly long time, red dwarfs could potentially host planets where life has ample time to emerge and evolve over timescales we can scarcely conceive. None of them have yet reached old age, simply because the universe is too young. That means the night sky of the far, far future will still be lit by these tiny, enduring embers long after brighter stars like our Sun have vanished. Over trillions of years, only the faint, red glow of these stars will remain. As the cosmos ages, the brightest, most massive stars will be the first to burn out. Blue giants and hypergiants live for only millions of years. Stars like the Sun last for billions. But red dwarfs, those small and efficient stars, will endure for trillions. Over these immense timescales, they will become the dominant sources of light in the universe. The galaxies of the distant future may glow only with their faint, ruddy light, creating a softer and far lonelier sky. Eventually, even these long-lived stars will run out of fuel, fading into white dwarfs and at last into black dwarfs. The universe will then shift from a bright, star-filled expanse to one illuminated only by fading embers. It's a vision of a cosmic twilight, where the last stars burn quietly, carrying the universe into its final chapters. For now, we live in its golden age, surrounded by brilliant suns of every size, color, and character. At the centers of most galaxies, including our own, lurk supermassive black holes, weighing millions to billions of times more than our Sun. Remarkably, stars can orbit right around them, tracing paths that test the very limits of gravity. In our Milky Way, astronomers have carefully observed stars racing around Sagittarius A, the black hole at our galactic core. One such star, known as S2, swings within just 17 light hours of the black hole, a cosmic hair's breadth. At its closest approach, it moves at more than 5,000 kilometers per second. Observing these frantic orbits allows scientists to measure the black hole's mass with extraordinary precision and to confirm Einstein's predictions about how gravity warps the fabric of space-time. These stars survive in a place where we might expect them to be torn apart, showing that even in the shadow of a black hole, the elegant dance of starlight can, against all odds, endure. When a star passes near a black hole, it isn't always destroyed. Sometimes it is flung away at tremendous speeds, accelerated by the black hole's immense gravity. These hypervelocity stars can travel at millions of kilometers per hour, fast enough to escape their home galaxy entirely. The Milky Way is known to host several such runaway stars, racing outward into the emptiness of intergalactic space. Their incredible journeys may have begun near Sagittarius A star, where gravitational interactions with the central black hole acted like a powerful slingshot. For any planets that might orbit such a star, the result would be extraordinary. A lone solar system, cast adrift and speeding alone through the cosmic dark. The discovery of these stellar exiles reveals how dynamic and chaotic galaxies can be, and how black holes can shape not only what falls in, but also what gets violently hurled away. To our eyes, a star often appears as a single, solitary point of light. But in reality, many are doubles, triples, or even larger families, all bound together by gravity. Binary star systems are especially common, with two suns orbiting a shared center of mass. Some pairs are so close they exchange material, while others are so far apart they may take thousands of years to complete a single orbit. To an observer on a planet in such a system, the sky might feature 2 or even 3 suns rising and setting together, casting multiple, complex shadows. A famous example is Alpha Centauri, our nearest stellar neighbor, which is actually a triple star system. By studying these pairs and groups, astronomers gain vital insight into how stars form and evolve. What looks like a solitary light in the night is often a hidden family engaged in a long, graceful, and silent dance. The death of a star can be the very trigger for the birth of new ones. When a massive star ends its life in a supernova, it doesn't just disappear, it profoundly reshapes its surroundings. The explosion blasts powerful shock waves into nearby clouds of gas and dust, compressing them and triggering new waves of star formation. In this beautiful, cyclical way, the death of one star can set off the birth of many others. Our own sun may have been born from such an event. Its original nebula enriched by heavy elements scattered by a previous generation of giant stars. These cycles ensure that galaxies remain fertile with starlight, continually recycling matter into new forms. Every brilliant star that dies leaves behind more than just ashes. It leaves the seeds of future suns, planets, and perhaps life itself. Stars don't simply end. They pass the torch, igniting the next chapters in the ongoing, magnificent story of the cosmos. While most stars that explode as supernovae meet a final end, a few defy all expectations. In extremely rare cases, a massive star may erupt violently, survive the initial blast, and then explode again years or even decades later. These unusual events are called pulsational pair instability supernovae. The star becomes unstable, ejects huge amounts of mass, then stabilizes temporarily, only to later collapse for good. Such stars shine unpredictably, producing multiple bright outbursts that can confuse astronomers into thinking they are witnessing repeated supernovae in the exact same location. These exotic stellar deaths highlight just how diverse the fates of massive stars can be, and how much we still have to learn about the limits of nuclear fusion and instability. In cosmic terms, they are stars that seem unwilling to let go, leaving behind a dramatic, flickering record of their final struggle against gravity's inevitable pull. Type 1a supernova are a special class of exploding star that shine with a remarkable consistency. They occur when a white dwarf star in a binary system accumulates too much matter from its companion, igniting a runaway thermonuclear explosion. Because these explosions always happen at roughly the same critical mass, their peak brightness is nearly uniform across the universe. This makes them standard candles, reliable beacons that astronomers can use to measure vast cosmic distances. By comparing how bright they appear from Earth to how bright they truly are, scientists can calculate how far away they must be. Type 1a supernovae played a pivotal role in one of astronomy's greatest discoveries, the accelerating expansion of the universe, driven by a mysterious force known as dark energy. They are not only spectacular stellar deaths, but also fundamental yardsticks that help us grasp the true immensity of the cosmos itself. Every atom of gold, silver, iron, and calcium here on Earth was forged in the heart of a star. When massive stars explode as supernovae, they blast those newly formed heavy elements out into space, enriching the interstellar medium. Over immense stretches of time, that material becomes part of new stars, planets, and living things. Without supernovae, the universe would be a much simpler place, filled mostly with hydrogen and helium. Instead, every explosion sows the seeds of complexity. The iron in your blood and the calcium in your bones were once carried outward in such a blast, drifting through the void for eons before eventually finding their way to Earth. Supernovae are violent endings, but they are also profound beginnings. scattering the essential ingredients of life far and wide. In this way, stars are both creators and destroyers, ensuring that the universe is filled not only with light, but with richness, variety, and the potential for life. It may sound like a beautiful piece of poetry, but it is a scientific fact. The atoms in your body were forged in stars. The oxygen you breathe, the carbon that forms your cells, the iron in your blood, all of it was created in stellar cores and supernova explosions billions of years ago, long before Earth even existed. Those elements drifted in the emptiness of space, awaiting their chance to come together. The phrase, "we are made of star stuff," captures a profound and literal reality. Every human being, every tree, every stone is a collection of recycled stardust. When you look up at the night sky, you are not just gazing at distant suns, you are seeing your own origins. The stars provided the raw materials, and in turn, we are the universe slowly, gradually becoming aware of itself. The connection between us and the stars is direct, tangible, and deeply, deeply humbling. Stars shine because of nuclear fusion, the process of fusing lighter elements into heavier ones. This process releases energy, but only up to a certain point. When a star's core begins to fuse silicon into iron, the balance shifts dramatically. Iron does not release energy when fused. Instead, it absorbs it. This means that once iron begins to accumulate in a star's core, fusion can no longer support the star against the crushing force of gravity. At that precise moment, collapse becomes inevitable, leading to a catastrophic implosion and often a supernova. The presence of iron is a death sentence for massive stars, marking the moment when their internal engines fail in a fundamental way. It's remarkable that this ordinary metal, so familiar to us on Earth, is also the cosmic tipping point that decides when giants of light will finally fall. A star is a cosmic balancing act held together by two opposing forces. Gravity pulls all of its mass inward, trying to collapse it into a tiny, dense point. Fusion, the burning of hydrogen into helium at its core, pushes outward with intense heat and radiation. As long as these two forces remain in perfect balance, the star remains stable. Too much outward pressure and it swells, too little and it contracts. Our sun has maintained this delicate equilibrium for billions of years and will continue to do so for billions more. But when the fuel at its center eventually runs out, the balance will tip, and the sun will transform into something entirely new. This eternal tug-of-war is the fundamental reason stars exist as steady, reliable sources of light, rather than collapsing instantly or blowing themselves apart immediately. Fusion is not just what makes stars shine. It is what prevents them from instantly imploding. Without the constant outward push of energy from fusion, gravity would crush a star into an incredibly dense, collapsed state in mere moments. Even our own sun, with its gentle yellow glow, is balanced on this knife edge every second. The continuous fusion of hydrogen into helium keeps it from collapsing under its own immense weight. For larger stars, this balancing act is even more extreme, with truly incredible forces in play. When fusion finally ends, gravity always wins, pulling the star's remains into a white dwarf, a neutron star, or a black hole. Stars exist only as long as fusion continues. Their light is a fragile, temporary victory against the relentless inward pull of gravity. Not all stars are as patient as our sun. The most massive ones consume their nuclear fuel at astonishing rates, up to 1,000,000 times faster. This means that although they are far larger and more powerful, They live incredibly short lives, sometimes lasting only a few million years. By contrast, our sun will shine for roughly 10 billion years. These fast-burning giants blaze with a fierce blue-white light, pouring enormous amounts of energy into space and shaping their galactic neighborhoods with intense radiation and powerful stellar winds. Their short, dramatic lives end violently, often in supernovae that seed the cosmos with heavy elements. The stark contrast between them and stars like our sun shows how a star's size dictates its destiny. The bigger the star, the shorter and more spectacular its life. They are the cosmic equivalent of fireworks, dazzling, brilliant, but fleeting, while smaller stars remain as steady, enduring candles across the deep, dark expanse of time. Our own sun, though stable and familiar now, has a dramatic future ahead. In about 5 billion years, it will exhaust the hydrogen fuel in its core. As fusion shifts to burning helium, the internal balance will change, and the sun will swell enormously into a red giant. Its surface will expand outward, likely engulfing the orbits of Mercury and Venus, and perhaps even reaching Earth. The sun's outer layers will glow a deep, dim red, far cooler than today's golden light, while its core contracts and grows hotter. Eventually, the outer layers will drift away into space, forming a beautiful, glowing planetary nebula, while the core shrinks down into a white dwarf. Though this transformation lies far in the future, it is a powerful reminder that even stars like our sun are temporary, following paths written into the fundamental physics of fusion and gravity. Our familiar, life-giving star will one day become something entirely different. On a clear, dark night, Sirius dominates the heavens as the brightest star we can see. Also called the dog star, it shines nearly twice as bright as the next brightest star, Canopus. Part of its brilliance comes from its intrinsic luminosity, but its relative closeness, only about 8.6 light-years away, makes it appear especially dazzling from our vantage point. Ancient cultures noticed and revered Sirius for thousands of years, linking it to mythology, calendars, and navigation. In ancient Egypt, its first appearance in the dawn sky heralded the annual flooding of the Nile River. Today, astronomers know that Sirius is actually a binary star system. The bright Sirius A is a hot, white main sequence star, and its faint companion, Sirius B, is a dense white dwarf, the remnant of a once massive star. To our unaided eyes, they blend together into one piercing, brilliant point of light. Sirius is not only a beacon in our night sky, but also a reminder that appearances often hide deeper, more complex stories. Long before the invention of the telescope, people across the world gave names to the brightest stars they could see. These names carried deep meaning, tied to agriculture, navigation, and rich mythological traditions. Stars like Betelgeuse, Rigel, and Aldebaran trace their names back to Arabic origins, while Vega and Altair come from ancient Arabic and Latin roots. In cultures from China and India to Greece and Egypt, stars were woven into stories that helped civilizations make sense of the heavens and their place within them. Even today, those ancient names endure, connecting us to the people who watched the very same sky millennia ago. Behind every familiar constellation lies a rich tapestry of human history, with names passed down through languages and cultures across the ages. While astronomers now use precise catalog numbers for identification, the old names remain, echoing across time. They remind us that our bond with the stars is not merely scientific, it is deeply cultural, stretching back to the very dawn of human civilization. Before the advent of compasses and GPS, the stars served as humanity's most reliable guides. Polynesian voyagers crossed the vast expanse of the Pacific Ocean by memorizing the rising and setting points of specific stars, steering their voyaging canoes across thousands of kilometers of open sea with incredible skill. The North Star, Polaris, which remains almost fixed in our northern sky, has long been used in the northern hemisphere to determine latitude. Arab traders, Greek sailors, and Viking explorers all relied on this celestial map to guide their perilous journeys. Even the seasonal migrations of people and animals were often timed by the positions of the stars. These sophisticated skills were passed down orally, with songs and stories encoding entire star charts for future generations. Navigation by the stars required extraordinary memory and observational skill, but it worked. Long before modern technology, humans trusted the steady light of the stars to carry them safely to new lands and new horizons. Today, those same stars still shine above us, though we now look to them more with a sense of wonder than out of sheer necessity. Polaris is famous as our current North Star, the one point in the sky that seems to stand still while all the other stars rotate slowly around it. But it has not always held this honored position, and it will not hold it forever. Earth's axis slowly wobbles in a cycle lasting about 26,000 years, a motion known as precession. This means the celestial pole gradually shifts over time. Around 3000 BCE, the star Thuban in the constellation Draco marked true north. In about 12,000 years, the bright star Vega will take its place. Polaris is simply the current chapter in a long, slow story of a shifting sky. Ancient monuments, like some pyramids and stone circles, were aligned to different stars that once held the northern crown. Watching the pole star change over millennia is like watching the Earth itself breathe across the ages. A profound reminder that even the patterns we consider fixed and trustworthy in the heavens are in a state of constant, graceful motion. If you could stand on a planet orbiting a distant star, the constellations you know and recognize would completely vanish. Stars appear grouped together from Earth only because of our particular vantage point in space. Seen from many light years away, their arrangements would warp and shift into entirely unfamiliar patterns. From a planet orbiting Proxima Centauri, our own sun would appear as nothing more than a faint, additional star in the sky, perhaps tucked into a new, unknown constellation. From the Andromeda Galaxy, the Milky Way itself would be seen as a glowing sideways band, while the individual stars we hold so familiar would be completely lost within its swirling, brilliant core. This shift in perspective shows us that constellations are ultimately illusions of distance and viewing angle. The night sky is not a fixed picture painted on a dome, but a deep, three-dimensional ocean of suns, and it will appear differently from every single shore. To imagine other skies is to realize how deeply our own view of the universe is shaped by the simple yet profound fact of where we stand within it. The constellations we know and love, Orion, Cassiopeia, the Big Dipper, are all temporary. Over thousands and millions of years, stars drift through space, moving relative to one another. Slowly, almost imperceptibly, the familiar patterns will warp and distort beyond all recognition. The hunter Orion may lose his distinctive belt. The Dipper may lose its familiar handle. Entirely new and unknown groupings will emerge in their place. To us, these changes are far too slow to notice in a single human lifetime. But on cosmic timescales, the sky is in a state of constant, fluid change. Future civilizations, or even future species, will inherit night skies filled with completely different star maps. The new mythology of their constellations will be unique to their time and place, just as ours are tied to the ancient cultures that first named them. The constellations we see tonight are merely snapshots of a fleeting, temporary arrangement. A beautiful reminder that nothing in the cosmos is permanent, not even the patterns we so lovingly draw in the stars. Gravity has the power to bend light, a prediction made by Einstein over a century ago that has since been confirmed. When the light from a distant star passes near a massive object, such as a galaxy or a black hole, its path can be bent and magnified. This phenomenon is called gravitational lensing. Sometimes it can split a single star's light into multiple images, or make it appear far brighter than it truly is. Astronomers have even observed individual stars magnified in this way, briefly becoming visible across billions of light years, distances that would otherwise be impossible to detect. Nature's own magnifying glass allows us to peer deeper into the universe than our telescopes could ever manage alone. It shows us that space is not an empty, static stage, but is flexible and dynamic, bending light in ways that reveal hidden cosmic treasures. Even the straight path of starlight is ultimately shaped by the invisible yet powerful hand of gravity. Constellations are human creations, patterns we trace upon the backdrop of the stars, but they are not eternal. As the Milky Way rotates and its constituent stars drift on their own paths, some of today's most recognizable shapes will slowly vanish. In about 50,000 years, the familiar form of Orion will be lost, its bright stars scattering to new positions across the sky. In a few million years, the Big Dipper will no longer resemble a dipper at all. To future observers, these constellations may not exist in any recognizable way. Just as ancient humans saw different star patterns than we do, the beings of the far future will inherit their own unique celestial maps. The constellations we know are simply temporary alignments, and the myths we attach to them are tied to a passing arrangement of stars. They remind us that the sky itself has a long and dynamic history, and that the maps we make of it today will someday be as outdated as ancient hand-drawn charts of the seas. Though the stars appear fixed to our eyes, they are in constant motion. Their immense distances make this motion nearly invisible over a human lifetime, but over centuries and millennia, the changes accumulate. This gradual drift is known as proper motion. Barnard's star, for example, shifts noticeably against the background sky every few decades. It has the fastest known proper motion of any star in our sky. If we compare ancient star maps to modern ones, we can see the slow, graceful shuffle of the heavens. Even the shapes of our constellations change subtly over the course of human history. This ever-shifting sky reminds us that what seems eternal and unchanging is, in fact, not. The stars are not painted dots on a static dome. They are suns, each traveling on its own unique path through the galaxy, carrying their own stories and histories, their light tracing elegant lines of motion across the vast canvas of cosmic time. Our sun does not remain in a fixed place either. It orbits the center of the Milky Way galaxy once every 230 million years or so. Along this grand journey, its stellar neighborhood continually changes. Stars that are near to us today will slowly drift away, replaced by others that are currently crossing our galactic path. In the distant past, the sun's closest neighbors were entirely different stars, their light mingling with ours to create a different, forgotten sky. As our sun continues its journey around the galactic center, the constellations around us will transform, and the stars we know today will gradually fade from view. This constant cosmic motion shows that even our sun's place in the galaxy is temporary. It is part of a grand, slow rotation that carries us and our stellar companions on an endless journey through space. To look up at the sky tonight is to see just a single, fleeting frame of that endless journey, a moment where our star's companions are, for a brief time, familiar. Globular clusters are dense, spherical swarms of stars, often containing hundreds of thousands of individuals packed into a relatively small volume of space. They orbit in the outskirts of galaxies like glittering, ancient satellites, each one a fossilized relic of the early universe. Many of the globular clusters associated with the Milky Way are more than 12 billion years old, making them nearly as ancient as the universe itself. Their stellar populations are generally composed of small, faint red dwarfs and long-lived giants, while any massive stars they once contained burned out eons ago. Viewed through a telescope, a globular cluster appears as a dazzling, tightly packed snowball of light, with stars in the center so crowded they blur together into a continuous glow. These clusters are more than just beautiful. They are windows into the distant past, showing us how the very first stars formed and lived out their lives. Studying them is like reading a history book written in starlight, one that traces the earliest days of our galaxy's formation. Hidden among the many younger generations of stars in our galaxy are a few ancient elders, stars that date back almost to the dawn of time itself. Some of these stars are more than 13 billion years old, nearly as old as the universe. They formed from primordial gas that contained very few heavy elements, the products of earlier stellar generations. Astronomers identify these ancient stars by studying their spectra, the unique fingerprints of elements present in their light, finding chemical signatures that have remained almost untouched since the Big Bang.